top-class problem solver. The goal of this video is to help us learn to analyze the problem and communicate our solution effectively. A mass, 0.25 kilograms, attached to a light spring, oscillates freely at a frequency of 0.32 Hertz. The amplitude of the oscillation is 0.50 meters. At t is equal to 0.1 seconds, the mass is at y is equal to 0.20 meters and is traveling in the positive y direction. Find the phase constant for position versus time in cosine form. The problem-solving method consists of 3 steps. The first step is interpretation of the problem. Then we devise a strategy, and then we execute our strategy. The first step of the interpretation is to identify the concept embedded in the problem. The fundamental concept in this problem is oscillation. So, in our solution, we write, this is a simple harmonic motion problem. The next step of the interpretation is to create the model and represent the model in a diagram. The fundamental components of the problem are the spring and the mass. So in our model, we indicate our spring and our mass, and we set up our one-dimensional coordinate system with the origin at the point of equilibrium and our dimension of motion, which I prefer to call y. The third step of the interpretation is to extract the data carefully from the problem. In the statement of the problem, the mass is given as 0.25 kilograms. The frequency of the oscillation is given as 0.32 Hertz. And the amplitude of the oscillation is given as 0.50 meters. We are also given that at time t is equal to 0.1 seconds, the position y is 0.20 meters, and that at the same time the particle is traveling in the positive y direction. So these data are indicated here. In addition to this, from part A, which we had calculated previously, we calculated that the angular frequency omega is 2.0 per second. If you wish to see how this is calculated, please refer to the video for part A. The first step of the strategy is to determine precisely what is required. In the statement of the problem, we are asked to find the phase constant in cosine form. So this is what we write and highlight in our solution. The second step of the strategy is to construct the concept map. The concept map relates the parameters that are given in the problem and the required parameter. The general equation for simple harmonic motion involves the amplitude, the angular frequency, and the phase constant. We know the amplitude and the angular frequency, so what we're left to find is the phase constant. If we apply our known position at the given time t, we will be able to find the phase constant, except that in this, as in most cases, we will actually find 2 values of the phase constant. The way to disambiguate between these 2 possible values is to apply the velocity information at that or some other time t. The third step of the strategy is to create an action plan based on the concept map. The first step of our solution is to apply our known value of position into the general equation of simple harmonic motion and that will give us the two possible values of the phase constant. The second step is to disambiguate these two values by applying the velocity information, and that will give me the unique value of the phase constant. The first step of the execution is to follow the steps of the action plan. So for the first step, we write down the general equation y of t, and we substitute for the known values of a and omega. We then substitute the value of y that is given at the time that is given, and when we have done that, we are left with an equation that contains only phi. When we simplify this equation, it looks like this. Cosine of 0.20 plus phi is equal to 0.40. Let us call the angle inside of the brackets here theta. So we have cosine of theta is equal to 0.40. Because this is a trigonometric equation, there are two possible values of theta. If the cosine of theta is, as given, positive, it means that the theta has two values, one in the first quadrant and one in the fourth quadrant. From the previous step, we obtained two possible values of theta. We now need to determine which value of theta is the correct one. In order to do this, we need the velocity information. We could do this step purely algebraically, but instead we're going to use a more elegant solution which uses the relationship between simple harmonic motion and uniform circular motion. When we use this relationship using what's called the auxiliary circle, we see that for a particular value of y in this simple harmonic motion, there are two possible phases of the motion. In the first phase, for which theta is in the fourth quadrant, we see that the particle is moving in the positive direction. For the other solution, in which theta is positive, we see that the particle is moving in the negative direction of y. We are given in the problem that the particle is at this instant moving in the positive direction. This therefore means that we should use the negative or fourth quadrant value of the phase theta. So going back to our previous line of solution, we choose the negative of the two values that we obtained, and then from that we derive the value of phi. The second step of the execution is simply to write down and highlight your final answer. So here we write our answer. Notice that the implicit unit of phi is radian, but because radian is a dimensionless unit, we do not need to write it explicitly. The third step of the execution is to check your answer. When you check your answer, make sure that you state clearly what is required, that you give the appropriate unit, and that the magnitude of your answer is reasonable. So the first thing that we verify is that what we have found is indeed what was required. The second thing we check is the unit, which, as we said before, is in radian. The third thing we want to check is the magnitude. The most straightforward way of checking the magnitude would be to substitute the value of phi obtained back into the equation that we started off with. One other check that we can perform is that we see that this expression here in brackets, which is the same as this, minus 1.2, this is approximately in magnitude equal to pi over 3. So when I take the cosine of plus or minus pi over 3, which is plus or minus 60 degrees, I will end up with approximately 1/2, which is close enough to what we have here. The reason we might want to perform this check is that the most straightforward mistake to make is that we have done our calculation in degrees. So we verify that this final expression is sensible when the angle in parentheses is expressed in radian. Here once more are the 3 steps of our problem-solving method. Thank you for watching.
Some people